stay here for 4 years, and like there could be more people
Wow.
potentially. Yeah.
Wow. Nice.
Wait, Max,
Yeah.
you're leaving at the end of the spring, right?
Yeah, in a few weeks,
Yeah. Yeah.
Yeah, and I'm leaving next year. I'll probably stay
Yeah.
until then.
Yeah. And I'm gonna stay for like 4 years. So.
Wow.
Yeah.
How long do you want to stay in here, Ethan?
Oh, I'll probably be here for another year at least. I didn't get into UC Leeds or any other summer stuff, so um, I mean, I don't know. What's the plan for Cal's fun this summer? Because if I can stay during the summer, if it works.
Yeah. I think it does get the funding from NSF something. But
So we're gonna
to
be
do
here during
some.
the summer?
If you choose to, yeah. Yeah.
Yeah, definitely. Yeah, I definitely want to do it.
Yeah. He had some funding for pay for us or something. That's good.
All right, yeah, yeah, I'll be here during the summer and probably the fall too.
Yeah.
I
Nice.
don't think anything
Nice.
else is gonna come up that's gonna take my time away.
Yeah.
This is very good.
Right.
Okay.
Let's see who goes first. Like I and Max can go first because like our representation is probably deeper,
Oh,
I guess.
mine's definitely not because I have a
I don't
midterm
know.
tomorrow. I have a midterm tomorrow
Okay.
morning at 8 a.m. It's ridiculous.
Yeah. 8 a.m. though.
I'm gonna go before Triet though, because I
Yeah.
saw it. I,
Yeah.
I feel like yours are more of an example and mine is more like just a basic introduction. I
Yeah.
guess
Yeah. Yeah.
more in the concept itself and the
All right. Do you want to go first, Jefferson? And
yeah,
then I can
okay.
go second. All right. Let's go.
Can you guys see my screen?
Yes.
Yeah,
Okay, so GN is like a supervised it's an generative unsupervised model that consists like two separate components, and there's an adversarial in part of its name because it's basically two components, two separate models competing against one each other and trying to improve itself. So the discriminative model it's a classification model, which is a type of model that will only give you two results, like true or false, one or zero, fake or real in our case. And this studies like boundary of the data set of what's considered true and what's considered fake data set. It's basically a way to analyze the pattern of like the data set. And the first step of GN is basically to train your discriminative model using the training data. And then the generated model is um, the goal of generated model is to create a sample that is very similar to the original data set, and you train the generated model by creating a random vector that seeds the generated process, and then that vector is converted to Latin variable into Latin space, just like all the other training data, and then um, within it kind of recognizes the pattern around it, and it uses that information to make observation on the training data, and it feeds back into generated model, and it starts to train the model to provide some sort of accurate data that's similar to the training data. And then the what makes this model special is the adversarial process, which is once both models train, it start improving each other with using the information. So generated model will create some sort of data set from its trained data, and then this will be combined with the test data that's split from the initial data set. And both is feed into discriminator model, and the discriminator model will check if it's like actually true or false based on what the training data, like previous trained data. And then if it's true, then the generator model will get the feedback that its data is not. I mean, if basically they're competing against one another, and if the generator model is not able to fool the discriminator model, then the generator model will get a new update. You'll get the feedback that and it will use this information to fix itself. And if the discriminator model cannot recognize the generator model, it makes up the data generator model made is true or false, then it will get updated. So I feel like for our project, this is mostly used to create new data set because I read through one of Ethan's paper that he posted in his slide, and it's basically high entropy alloy discovery using machine learning. And then I found out that they also use GN model, deep generated model, to create new data based on the initial data set, because usually our data set is it's we don't have much data because of how hard it is to compose materials, which is why that it's important we can use this method to generate a similar data set to enlarge the sample size, and then using other types of model, we can analyze the pattern better and then test for more, and then test on it. But there's a problem that we could create more biased data set because all of the data is based on the original data, right? So, and that's pretty much it for this one, for my presentation.
Awesome. Any questions?
So I have one. So with generative adversarial networks, is there two autoencoders, one to generate and one to test?
No, I think both of them are put together, but they're like conceptually they're separated into two parts. I never tried it. Have you, when you did the CAD model, are they separate or are they together? Like,
They are two separate neural network and they're not autoencoder. Autoencoder is when you have the latent space much smaller than the input and the output. But in this case, it's just two separate neural networks.
So they're both autoencoders, right?
No, they're not autoencoder. They are neural networks, but they're not autoencoder.
Wait, so are there two latent spaces in four, or I'm trying to understand the common like hourglass shape where there's an encoder, a latent space, and a decoder?
Oh yeah, that one.
Are there two of
Not
those for the
not
gains, or
not really. It's just two neural network. I think you should separate them. It's just two different neural network. One to generate new data and one to discriminate the data. It's not for decode or anything.
yeah.
okay?
Yeah, it's a whole separate idea from the autoencoder.
I think this is more like this is more like a method to, it's not really like identifying, like trying to predict like a pattern that what we're trying to do with the
Mhm,
machine learning. It's like this is like a way to like enhance the data set.
mhm. Yeah,
So it's more like a supervised model, honestly, because
it is.
it's,
Yeah.
yeah, and it's not, so it doesn't really have to do with latency. I guess to do it on its own, but it's not really part of the main idea.
Yeah, it's just in the very beginning we used a noise data. Like we don't even use much idea from autoencoder. It's just a whole different approach of the generate new data, right?
Mm.
The the common question concern.
Go ahead,
Yeah,
Triet.
right. My turn there. Uh, um, you can see my screen, right?
Yeah.
Okay. So, okay, here you go. Generating cat face images using GAN. So, I use the GAN model to generate new cat face. So just an overall of this presentation, we're gonna go over the data set. So where I get the data from, the architecture, so how I build the neural network, and how many neural I use, what's the activation function, what's the loss function down here, and then training process. So how do you train a GANs model? And I can show you the results, which you already saw last time, but and also this template is generated by ChatGPT. So I put in ChatGPT going to tell me to go this presentation, this overview right here. And for the goal, we're gonna try to generate realistic cat face, but also at the same time, through this project, I hope you guys can learn more about the GANs model. For data set, I use cat faces from this link. You can click the link and then you can have this. You can just download from it, pretty much. Download over here. I chose this because they already have the code for generating cat face and like they have a data ready. So everything's ready for me to use. For data set, so before for the data to process the data, I download it to my computer, right? But then I talked about you guys before. So the CPU, GPU, and TPU. CPU is computer processing unit, which what your computer is using right now. And it's not very strong. It's helpful, but it's not very strong because the fundamental calculation is scalar a product. So it's taking one number with one number. The GPU is the graphic card in your computer. It's more powerful because it's taking its fundamental calculation is using vectors. So vector dot product between the vectors is the fundamental calculation. Then TPU is a very strong the hardware to calculate, to do the computation. It's very powerful. Its fundamental calculation is matrix multiplication. This is the most powerful one, but then we don't have access to it, and it's not very popular. So in this case, I want to use GPU because CPU is popular, but it's too weak. It's not strong enough to um, train the GANs model. I want to use the GPU to train the GANs model. But then I failed to switch my computer to GPU somehow. I failed. So I had to switch to Google Colab to do the coding. And while Google Colab, I have to upload my data set into Google Drive. And after that, after upload to my Google Drive, I have to mount the Google Drive to the Google Colab. So here I see from Google Colab import drive and then prime mount content drive. So mount this file, coding file to the Google Drive over here on the left side. Then you can see I have a directory. So to go from content first, you go to drive here, then share drive, then calendar grad group, then coding, dataset, cat, cat, stop at cat. The one folder before the cat face, which is one folder before the real data. And once I import all the data, so for the architecture, so we have this quick recap. So you have random noise, the military generator, and it's kind of misleading, but it's not actually this architecture. But as a military generator, you get a fake image, and then you're gonna input either the fake image or the real data, the training set, into the discriminator. If it's real, it's gonna spit out real fake. And then you're gonna check if the generator is successfully fooled the discriminator or not. And then it's a game between two players. If the discriminator wins, then the generator loses. And if it loses, then it has to update itself. And then same idea. If the generator wins, then the discriminator loses. And if it loses, then it has to update itself. And then one of them become better and better later every time. And then the image become realer and realer. That's the idea. So for architecture of generator, we have 128 narrow in the input because that's the size of the image, 128 pixels, and then 64 times 64, I believe. And then we go to a bigger neural network, the hidden layers, going to be 512, and then you go down to 256, then down to 128, and then down to 64. I'm not exactly sure why they construct it this way, but this is what they presented in the code, in the sample code. For activation function, they use rectify leader unit activation function. What that means is that when about neural network is simply a what is it? Linear combination. So you times all the input, times the weight, then you add them up, then you plus the bias, and that's the output of the neural network. For this case, if you add all the weight and plus the bias, if that output is less than 0, then negative number, then the output is going to be all the way 0. Then if that output is greater than 0, then it's going to output that exact number. So that's the rectifier leader unit. For they use CNN, which is convolutional neural network. And probably Max know more about this because he introduced me to this in the beginning. But instead of, so the idea of neural network, right, is all the input times the weight and you sum them up. Instead of take to consideration all the input in the input layer, what they do is they only take a look at the very specific input. So which is in this case 9 input right here and times the weight and then equal the output. And then they move on. So this 9 input right here is correspond to this output right here. And they move on, continue moving on to the right until they go through all this. Do you see that? And here's the code. So we look at the code, you're going to see this is the latent size, which is 128. We go back to this. So this is latent size, 128. And then generator sequential is how you do the construct the neural network in Python. First you have convolutional transpose, and then which is I guess just refer to this CNN, and then latent size, which is the first layer, 128. Then 512, which is this layer right here, 512. And kernel size 4. I think this one is referred to this one. So this over here is a 3 by 3. And then 4, which means it expands to 4 by 4. And then stride 1. Stride is just a step it takes. So normally this one gonna take one step to the right, one step, one at a time until it runs all over this image. Then padding equals 0. Padding is because when you do this, you can realize that the first input and output, they off by 1 dimension. Like this one at the corner already, right? If you put this at the corner already, then you have 9 input and like this outside have no number. You have to push it back. You have to add another like row at the top, another row at the bottom, another row on the left, another on the right. That's the idea of padding. In this case, they don't do any padding. And then bias false, so there's no bias in this case. Then they normalize it to 512. I think they normalize it to make sure all the noise data and everything is in the right dimension. And then ReLU is just rectify linear activation function, which is this one. If it's less than 0, it suppresses 0. If it's greater than 0, then it's equal itself. Okay. Then they repeat 512 to 256, 512 to 256, and then 256 to 128, and then 164. Same here, they go from this to 64. Then after that, tab 3 over here, and 3 is for color. You can get any color from 3 fundamental color. And that's tangent. What is the this one? I think this is going to scale. Oh yeah, it's going to scale the output into the value between -1 and 1, because I think that's the valid range for the pixel color. And for architecture, for the discriminator, same idea. Go from 64, 128, 256, 512, and then to 1, because you only care about either is correct or not. And you compare the architecture of the discriminator like this, you can see it shift this 512 into the right, like a little bit, which is something worth considering. I don't know why though. For the activation function, they use, instead of the regular rectify linear activation function, they use a Licky rectify linear activation function. So the only difference is that if it's less than 0, instead of flatted out to 0, they have a small slope, negative, positive slope. It's just a little bit different. And then the rest is the same. For the code, here they construct the neural network for discriminator. You can see 3 to 64. 64 is 3 is just the 3 color, 3 fundamental color to make up alternate color. 64 is the first layer we have. And then 64 kernel size, again, kernel size is just this one, 9, from 3 to 3, that becomes 4 by 4. Stride 2, so you go to the right 2 unit instead of 1. Then padding equal 1, which is you have to add a to another row on the top, another row bottom, then the column to the left, another column to the right. No bias. You normalize the data. And this is the activation function. And you have 0.2, which is the slope of this. And in place two, I don't know what it is, but anyway. And then they continue to repeat this with 128, then 256, and then 512, and then go straight to 1. Then they flatten it out, they reshape it into one-dimension vector, and then they squash the output into the range of 0, 1. So it's either true or false. And maybe in between you can take into the error loss function. For loss function, I took a look at the code and I see the binary cross entropy like in all of the code. Is keep looking at binary cross entropy. By the way, there's a function for trace generator. So you have a function for, not really a function, you kind of define the neural network for discriminator here. You define the neural network for generator here. And then you have a function to train the generator and function to train the discriminator. Train the generator, so you, no, see, clear generator gradient equal this. Yeah, mainly just run it through it, and then you have a loss function. For loss function, it's probably like the most important thing. Anyway, I got all the, so take a look at all the loss function at binary cross entropy. I didn't really understand what it means, so I shut up the internet, and here I got explanation, drift explanation. So you take out like all of the context and just think about a simple neural network. And this is the input, 0.1, 0.5, 0.2. This is all the input. And the times sum of the weight. And you add them all up, you have the weighted sum. And because the weighted sum is less than 0.5, let's say, that is going to be output 0. If the sum is greater than 0.5, it's going to output 1. And this is the real output. This is the output that's generated by the neural network. So in this case, the binary cross entropy is calculated by this function right here. So negative y times log of weighted sum plus 1 minus y, then times log of 1 minus weighted sum. So in this case, if you take a look at this first line, you're going to see the loss going to be calculated by negative y, which is 1 in this case, times log of weighted sum, which is 0.26, plus 1 minus y. So 1 minus 1, 0. So this one cancel out. And you get this 0.58 as the loss for if you use the binary cross entropy. Once you do that, you're going to see that if it's false, then you have a really big loss. If it's true, then you have a really small loss. So it's more penalty to the loss using the binary cross entropy, which is, I think, helpful for our case because you're generating more image, need to be really real. For training process, so mainly it's more about loss over here, optimize the loss, right? So you have a loss, bunch of loss list, and then you just put the discriminator and generate it in, optimize them. Then you run the epochs, put the image in and run them. And you append the loss. And then also they have the real scores and fake scores in this case because it's simply a two-player game. And then this is the epochs, and then they save the generated image and return loss. Mainly just for neural network, I feel like it's all about minimizing the loss, and then it's just up in itself until it minimizes the loss, and that's pretty much it. For result, is the result go from oops. And you can see the first one is just the latent space is some noise data. There's nothing special about it. But when it's playing the game, it can already after the first one, because the binary cross entropy, the loss function creates very dramatically. And you can see the cat face already. I get better after color on, better and better. Right. It's already at the cat face. And like to some point, you can't even tell the difference anymore. Of course, there's some photos that are not good, but until like epoxy is 40, it's already so good already. Like, you can tell the difference already. Right. Just keep running until I hear. Yeah. All right. And that's the end of my presentation. Any comment, question, concern?
Very good. Very thorough.
I was a bit lost when you were discussing the code and the functions.
Yeah,
I mean,
it's
I
fine.
probably haven't done this yet, so I don't really know what to look for, I guess.
Yeah.
With one thing though, so it's different. It's kind of early up with the vector and the tensor stuff. Is that basically just more complicated computers can do more data at once? Is that sort of what that's showing?
Yeah,
That a
it's different.
TPU can just compute more at once than a
Yes.
CPU.
Yes.
I've never learned. I know my thing's a bit different. But is learning tensors, is that valuable to understand or to program?
I mean, this is
Like,
not
is
that
it like vector?
it's not that important to understand, I guess. But
Okay.
yeah, just this is the thing. It doesn't explain why I'm using Google Colab and stuff like that.
Okay, yeah, because they use tensors or TPUs, right?
Yeah.
Okay, cool.
Right.
Very thorough. Okay,
Who's
the
next?
next one, I can go Ethan. Mine's not very thorough because I have a midterm tomorrow morning.
Mine's not super long either, but I think mine is I don't know, I think it's thorough, but it's not very long.
Okay, I'll just go first because I have like 4 slides. Oh boy, it's my last midterm of undergrad tomorrow. I cannot wait. Holy cow. Yeah.
Can you bomb it though? Like it's the last midterm.
What?
Can you just bomb that class? Because like it's not gonna affect anything, right?
It's a I can, but I kind of don't. I don't know. I have a 4.0 like this year, and if I get
Oh,
an A on this one, I should be able to clinch a 4.0 for the entire year.
whoa.
Don't
But he,
bomb it.
No,
yeah.
yeah. So like I'm just we'll
Do
see.
you have senioritis?
Oh, dude, I'm hella burned out. I feel like when you like get I don't know like this into it, and then you're like God damn, like I'm so sick of school. It's fine.
What kind of classes are you taking in senior year?
I'm taking MSc 190, MSc 141, and MSc 189 senior design.
Wow.
Basically, you just end up taking all because material science is so small, you end up just taking all the material science classes,
Wow.
like every single one of them, almost. That's midterm here. It's material selection, nanomaterials, and senior design.
I know it's this though. Ethan is chemical engineer, right?
Yeah, I am.
And then Jefferson, what?
I'm
Yeah,
mechanical.
mechanical. I see. Okay, I'm gonna be closest to you. Yeah.
My specialization though has a lot of overlap with material science. That's why I was attracted to Cal's group.
Are you taking a minor for materials science, Ethan? I know a lot of people
My
do.
minor's computer science,
Oh,
which
wow.
also fits in with this. But the problem is that I've had scheduling conflicts, and a lot of those classes are really they fill up really quick. So I might not be able to finish it, but I might be able to get some stuff done before I graduate.
Oh, nice.
So yeah.
Yeah, those classes are kind of crazy to get into. are super hard to get into, like just sheer volume wise. Okay.
Right.
Anyways, let's do this real quick. So variational autoencoders. Everyone knows what an autoencoder is. We've been studying for like the past few weeks. But basically, what an autoencoder does, that takes in data, and then it brings it down to latent space, the 2D stuff, and then it tries to recreate that data, right? However, there comes to issues with that, right? Because sometimes the data is pretty, especially, is pretty distinct, and this latent space may not be continuous. And like, what does continuous even mean? A good example is over here. I think Ethan, you also have this graph on your presentation. So TLDR.
Yeah, I think we're going to be presenting pretty similar things.
Yeah.
Is this from like the Towards Data Science?
Yeah.
I think we use the same source too.
Yeah.
It's a really good article though.
It is. So from my understanding from this article is that autoencoders will make hard decisions on like compressing data. So for example, when you have a 7 and a 1, right? But then oops, wow, that label is wrong. Variational. Yeah, we'll make hard decisions on what's on 1 or 2 or 3 or 4. But what autoencoders do is that they will basically instead of sampling or taking in discrete values for compression, they will take a probability of that. So this is kind of how that works. So for example, we're trying to directly encode data. Autoencoders will go straight from one image to another image, basically one image, compress it down, then spit out that image. But variational autoencoders will kind of take a probability of the data around it. So it's going to take a spread, like a mean. That spread is usually like it's consisted of a mean and a standard deviation of that data. So we have a more generalized data set. So what does that actually mean? So let's take a look at this example of like pictures. So if we take a look on the left, right, if we want to rate like what is a smile, obviously the kid on the left, he's not very smiling, but that's assigning the autoencoder here is assigning a specific value for his smile. But if we can get a lot more general and have a probability distribution of that data, so this kid is not he's not a negative 0.5 in smiling, but he has a most likely chance of being a negative 0.5 in smiling. And I think you could probably explain this a lot more, but when you go over it. So because of this probability, it allows us to recreate and make new data a lot easier because we aren't constrained by these discrete values and we have a more distributed spread. That's basically all I have. I think that the main point about autoencoders and variational autoencoders is that the data for variational autoencoders it's taking a probability, a statistical probability, rather instead of specific, data points. And I think Ethan, do you want to continue on that? That was pretty much it.
Yeah, I'll get my my slides. I'll share my screen. Okay. All right, how's that?
Yeah.
You can kind of see. Hold on. No, is it fine the way it is, or do you want me to try to just have it on just the screen?
Oh, it's fine. It's up to you. Whatever's easiest for you.
Hold on. Okay, hold on. I think this works.
Yeah, that works too.
Okay, so my presentation is about variational autoencoders and why they're very important, and why they're better than regular autoencoders. So, autoencoders. Okay, this presentation is a bit crammed, but I think I need to show everything. So basically, what they are is that they're neural networks designed to create models. What they do is they take a bunch of input data and they compress it into something into a space with smaller dimensions called a latent space. And then this is then extrapolated back with a decoder to try to create an image. And this latent space will contain the more important patterns that you can then abstract the broader image out of. The thing is, though, is that you got to train this data, and you have to have a cost function that compares the inputs to the outputs to make sure that latent space is looking for the more important features. And so you got to train it for it to work on a specific data set. So with regular autoencoders, what you're basically doing is you're trying to create a way to generate new images, but you can't really extrapolate any interesting thing out of the latent space because it's just designed to create new images. So what will often happen is that latent space will have many clusters, in that you'll have dissimilar data points right next to each other. So you can't just find the midpoint between two data sets to extrapolate what they would be, because it could be something completely different. And so that means they're not very good at making models. So the way you do that is you got to find a way for the latent space to be smooth and continuous. So what you do is that instead of latent space being like an n-dimensional vector, that's basically what they are. It's basically a vector has n dimensions and differing values depending on where you are in latent space. You make it two of them, one for the means and one for the standard deviations, and that forces it to be always continuous. And it makes interpolation a lot easier. So you can see with my slides, I'm showing the data point. Can you see my mouse? My mouse, can you see it? Okay, yeah, so this is just a regular autoencoder. It's just a discrete data point, and this is showing the vector describing its position in latent space. But this is for a variational autoencoder. You have also the mean value, but you also have the spread, which is measured by the standard deviation. So you can see with this chart, you can find an interpolation between 2 and 1, unlike the previous slide, where it was just 7 and 1, and you don't know what's between the two. Max said that slide too, actually. Okay, so are they harder to make? Yes, they are, because the cost function, in addition to just trying to get the inputs and the outputs to match, it also has to get the data to cluster in a meaningful way to make interpolation more accurate. So it uses something called the, oh my gosh, I forgot what it's called. It's a very long name, but I call it's KL divergence function. Max, do you know what it's called? I forget.
Second.
I should have remembered this better.
It's a great question.
It just would have made my presentation more crammed than it already was.
Kullback-Leibler divergence.
Yeah, that's it. Yeah, I think also I have it displayed on the very bottom. So what it does is it makes sure that it measures the discrepancy between the two probability distributions and ensures that they're normally distributed as well. And so it tries to coax the data to cluster to get in one cluster instead of a bunch of separate. Because if you have separate clusters in different parts of latent space, and you have a data point that you're trying to interpolate between them in an empty spot in the middle, it's going to be harder to find an accurate value. So it tries to get like the data like below. I'm showing this is just one big cluster, and then on the top slides I'm showing how it's better to get those data points close together so that their distributions are kind of overlapping. And then I have the divergence function right here at the bottom. So what they're currently used for is to create synthetic human faces, because you can basically do is you can try to fine tune what you're exactly looking for by selecting different spots in the latent space and then decoding it. You could also create synthetic music. I have a link. I don't know if it's gonna work, but I try that after. Oh, hold on. And then it's used for language modeling. So I have I copy pasted this over. What it's simulating an email, I think, and it's basically showing that there's the top model isn't as good and the bottom model is better, but they're both variational autoencoders. And then they're also used for language for radiology. I'm not entirely sure what this picture is describing. It's been a while since I put this together, but I think it's basically going to find more meaningful patterns in the data that you feed it. And so this is important for what I want to do, because with the paper we have, it also uses a variational autoencoder. It uses a Warsenstein architecture. I'm not entirely sure what that means. Triet probably knows more than I do. The problem with the autoencoder in the paper is that it's just a function of composition. what it does is it takes the composition and tries to find meaningful patterns. And then on top of that, it will use a physics-based function to estimate what the TECs will be as a function of composition. And then it will use linear interpolation to find where the TEC will be lowest. And then it will use latent space to try to find what value that would be and the composition it has. And then it will have a bunch of candidates from that area. And then it ultimately wants those to be tested experimentally to see if the values are low enough. I think we can get it to be more accurate by making the latent space a function of the TEC. So that's something that I've kind of looking forward to doing right now. And that's it. So those are the major sources I used.
Nice.
Does that all
That
make
was
sense?
good.
Any
Yes.
questions?
Do you mind going back a few slides to the just going back another slide. I think this
That one?
one. Yeah, this one. Let's see. Uh for the top like figure on the left and the right, and you might explain them more. I kind of don't get it.
For this one?
Yeah.
Or you need it zoomed up more?
No, I mean like why, like what's happening on the left and what's happening on the right, and like which one do you prefer, stuff like that.
So this would be like if you did not have if your loss function did not also try to get the data to cluster, if it just focused on making the inputs and the outputs similar, it also has to try to get the data to cluster.
Sorry,